Sure, yeah, I'm ready to go. Cool. Okay, so is the recording already recording? Okay, so yeah, welcome back to the second part of my K-theory talk. I promise this is going to be the last part of the K-theory talk. We're going to pick up where we left off last time. What I was trying to get to is talk about products in K-theory, and particularly we want to compute something called Bott periodicity. We're not going to compute it, I'm just going to state what it is, because it's very, very hard. But the result is going to be, we'll have values for the K-theory of all of the spheres. This is going to be one of the things that we're going to call Bott periodicity. There's actually many, many incarnations of this result. And they're all very important and goes into the actual proof of the Atiyah-Singer index theorem and even into the statement of it. But we're not actually going to prove anything. It's going to be challenging enough just to get a statement out of it. So part 2 is going to be an introduction to what is the Atiyah-Singer index theorem from the context of K-theory. We're going to have to really speed run what is an elliptic operator in order, and a few other things in order to talk about what is the actual topological index. And then the content of the Atiyah-Singer index theorem is going to be that, okay, there's a certain number associated to Fredholm operators. The topological index is also a number. The theorem is that these two numbers are the same, which is kind of an innocuous statement, but when you see what goes into it, it's very surprising. And if we have time, I'll write down a formula for the cohomology version of the index theorem, just because it looks terrifying. And but you can actually get actual computational formulas out of that. It's very useful. So we're going to start sort of with the hope that everyone remembers all of the K-theory stuff from last time, but if people have questions, I can just remind everyone. So we'll start with products. So in our first talk about vector bundles, we talked about if you have two bundles over the same space, you can take their direct sum, you can take their tensor product, and things like this. Another operation that you can do when you have two different spaces is take a sort of external tensor product. You could also do this with direct sum. There would be an analogous operation. All that you do is you specify over x and y. Just take the fiber over x, tensor the fiber over y. If you'd like, you can pick projection maps, pi x, pi y, and this is really pull back the bundle V to the product, tensored with pull back the bundle W to the product along the respective projection maps. And that's not what I want. I want our projection maps to go like this. Pi x, pi y, have a V, have a W. Right, so each of those two factors you can pull back to the product of x and y and just tensor those two bundles together. That's what we're going to call box times. From box times, you can recover the internal tensor product of two bundles over the same space by mapping your base space into the product with itself along the diagonal map. Then you can just read off, these are just going to be all of the pairs where x and y are the same elements. So you're only tensoring things together over individual points in X. This, you have to verify, but you can check that this does give a bilinear map on K-theory. So you take a K-theory element of X and a K-theory element of Y. You can form a sort of exterior product in K cross Y. And for whatever reason, I'm going to call this sharp. The reason is because this comes from my source. I should actually write this down. It's called a lecture course on index theory. And it's by my advisor, Johannes Ebert. And they're not the best notes because it's lecture notes and they're not very polished, but I'm using it because it's my most thorough exposure to K-theory, K-theory and index theory, so it's just the thing that is easiest for me to learn from, even though I find it's really disorganized and kind of hard to follow a lot of the time. But he uses sharp, so we're going to use sharp here. So giving a bilinear map means, by definition of the tensor product, the universal property means we get a linear map, like this. So now this is linear. Okay, so given this exterior product, we get right away an extremely important result, which looks a little bit too good to be true, and it sort of is. If you take y to be S2, just a two-dimensional sphere, so we remember, I think this is this. Yeah, so take the two-dimensional sphere. We had that the reduced K theory of the two-dimensional sphere was just equal to z, where the generator is given by this thing called the bot element. So this is generated by something we call bot element. And so the unreduced K theory would just be another copy of z. I don't remember if this is right or not, if I really want the reduced or unreduced. But the next statement is going to be more true, then I'm sure the next one's true about relative K theory. So I just don't remember exactly if this is supposed to be reduced or unreduced. But there is a product theorem coming from taking the product with, in specific, the bot element is what induces this isomorphism here. So this exterior product also extends to a relative product. So if you have two pairs of spaces, and let's call them good pairs, which meant, just like last time, that both x and y are compact Hausdorff, and the subspace here is closed, so that in particular it's also compact in Hausdorff. So we're going to define the product like this. You're going to start with x and y as the main space, but the subspace that you're relative to, you're going to do sort of like a distributive law. You're going to take x times b and union that with a times y. So depending on your situation, these two subspaces might not be disjoint. And actually, if they're both non-empty, well, yeah, depending on the situation. In fact, they probably are almost never disjoint. So if you remember last time we had relative K theory, we defined to be triples, E0, the homomorphism to F0, so that the restriction to the subspace is an isomorphism. And similarly on the other one, E1, so I can just use the i's here. So we had this notion of K cycle, a relative K cycle. Turns out if you, so what you can do with these is treat these as chain complexes, just of length 2. And you can take their tensor product as chain complexes. And you have to make sure to use things like the Koszul rule in order to get the differential with the right signs. But you can do this, and then as we saw last time, if you have some sequence of spaces, vector bundles and morphisms between them, which are exact over a certain subspace, you can take up this wrap up function to turn it into just a pair of bundles with one homomorphism, which is an isomorphism over that subspace. So it turns out that this is the correct subspace to take, so that when we tensor these bundles together, we get a chain complex which is exact over this subspace. So this is a big, big check to see that the wrapping up of these two complexes actually gives you a K cycle for this pair. So it's actually an isomorphism over the subspace. And from the formula I gave last time, it's sort of an exercise to write this down. It ends up just being like a 2x2 matrix expressing the, I'm not going to go into it. It'll just be too confusing to try to stumble through that. I'll leave that as an exercise from the formula I wrote last time.
Can you remind me what was the wrapping up thing again?
Yeah, so let's say we have a sequence E dot, D dot, right? I did it like this. Yeah, it's probably worth bringing it up again because you have to point out that you actually have to choose a metric to get the adjoint of D. So each of these maps, we're going to get an adjoint dk star. And so let's say this is exact over A subset of X. And then the wrap up is you take all of the even elements, so 2k, mapping to all of the odd ones. And you sort of, you add together all of the differentials and their adjoints that have the proper domain and codomain. So everything coming out of an even thing, you take D. So you take the sum of all of the even D naughts and all of the odd adjoints. So the adjoints of the D k plus ones. So maybe even write something like that. What's the best way to say this? 2 bullet and 2 bullet plus 1. If that makes any sense. Yes. So you come up with this D plus D star going from the even degree things to the odd degree things. Is what you do. So your formula for what is the actual the combined phi is going to be expressed in terms of the phi's and the phi stars in some like 2x2 matrix in this case. I don't need this yet. Okay, so as a special case, as we saw last time, or as I mentioned last time, if you take a single point and take K-theory relative to that point, that's the same as choosing a trivialization at that point, which in a roundabout way, this is giving us the reduced K-theory of X. So if we choose our base points for our subspaces, we're getting something defined on reduced K-theory. And when we go over here, what is our pair space? It's X cross Y. Now we're getting X cross the base point of Y, union the base point of X cross Y. That's just one copy of X and one copy of Y meeting together at a single point, which is the base point cross base point. So that is by definition the join. Sorry, not the join, the, why don't I remember?
Is that the wedge?
Wedge, did we just call it wedge?
The wedge sum? Gosh.
Yeah, that's the wedge product. So many. As a lattice, this is the join symbol, so I always get confused. And in geometry, this is a wedge. So
Yeah.
it's not great. Okay, so what we get then is we're going to the reduced K-theory, right? And so more generally, we also had the K relative to A was the reduced theory of K tilde of X mod A for good pairs like this. And so X cross Y mod X wedge Y is called the smash product. If you haven't seen this before, you could take this as the first definition. This is what it is. So the relative product theorem says, if we take Y as S2 again, this is telling us that if we take reduced K-theory of X, tensored with the reduced K-theory of S2, which now this is, right, this is Z generated by the bot element. This is just one copy of Z, and so the tensor product is naturally isomorphic to just the reduced K-theory of X. A product with the bot element being an isomorphism onto K tilde of X smash S2. So this is something I mentioned 4 weeks ago, so maybe not everybody remembers, but X is a pointed space. Just write X. That the n-sphere smashed with X is homeomorphic to the n-fold suspension of X. Which, if you don't remember, this is the, how do we say this? Well, you define it inductively to be the suspension of the n minus first suspension of X, where the suspension of Y is you take the interval on Y, and you mod out by crunching up the top and bottom ends. So Y cross 0 relative, yeah. We'll say it like this. Any pair Y comma 0 is equivalent to any other Y prime comma 0. Similarly at point 1. And you also want that the base point of Y, there's an entire line emanating out of that, and you want to crunch that all down to a single point. So this is a fact. You can draw pictures to convince yourself. In this particular case, we're just getting here the two-fold suspension of X.
I have maybe a question.
Sure.
At least my definition of wedge product is usually like when you have pointed spaces, you take this product like X cross Y, and then you mod out by the relation X not equal to Y naught. But here you're looking at it as a subspace of x comma y, x cross y, right?
Yeah, I've never seen that expressed as a quotient before. So for me, I've always seen, by definition, the wedge product is
Like think of
x. Yeah. So you take x disjoint union y.
yeah.
Modulo your base point is the same as that base point.
Also,
Is that what you were thinking about?
yeah, that's what I'm thinking. So you're just
Yeah.
identifying. I'm just thinking of like in the diagram. I was thinking like a line in x, a line in y, and I'm just thinking of this as a subspace.
Yeah. So it's like if you have R1 cross R1, like giving you R2,
Yeah.
right? You still have your R1 wedge R1, where your base point is 0, 0.
Okay.
Yeah. So yeah, if you choose like any A in R1 to be your base point and your B in R2 to be your base point, and your join would be like the pair of axes going through the line AB.
Okay.
So yeah, just depending on which base point you choose, you'll find a different copy of the join inside of the product, wedge inside of the product.
Okay.
Yeah.
Not topologist. I want to make sure I understood the.
Yeah. Well, yeah, it took me like a little while to figure out why is the join, why is the wedge in there? Where did that come from? Yeah. It's a nice construction. Okay, so that's our relative product theorem. So in particular, do you mind if I get rid of this drawing? So let's look at something interesting. So in particular, for x, say if x is a sphere, Sn, what do we get is k tilde of Sn multiplied with bot class gives us isomorphism with a sphere of degree 2 bigger. So close, equals 2. And so in particular, we have a complete answer now, given bot periodicity, this relative product theorem, which is very difficult to prove. You get an answer for what is K-theory of spheres. You get that it's Z, n is even, because starting at S0, just a single point, the reduced K-theory of S0 is the same as the unreduced K-theory of a point, which is Z. And we saw that for odd degree spheres, like the circle, the reduced K-theory was 0. So this is another way of stating Bach periodicity that people tend to say. There's kind of a lot of statements that go by the name of Bach periodicity, and they're all sort of the same statement. This is the one that highlights that for spheres, it only depends on the dimension of the sphere modulo 2. There's this 2 periodic behavior in the K-theory of spheres. So then we get like we go to a slightly more esoteric version of Bach periodicity, the homotopy theory version. So recall we had this representability of reduced K-theory for good pairs anyway. K tilde of x was bijection with pointed homotopy classes of maps into this classifying space we called BU. So this was this co-limit of all of the BU n's as n increases. So this is saying, since this is the same as, right, what this is saying is that this class, homotopy classes of maps, are the same as mapping the two-fold suspension of x into BU. So this line is Bach periodicity. Or rather, it's the relative product theorem. And there is a topological phenomenon called the loops suspension adjunction, which says that for any two-pointed spaces, if you map the reduced suspension of x into y, this is the same as mapping y into the loops, x into the loops of y. So you can see this sort of geometrically. I'll just do it here. So how do you draw the reduced suspension of X? So you start with the cylinder on X. Let's say here's our base point. So we want to collapse down, oh, I can't use colors. Could be good. Yeah, we want to collapse the top and bottom circles. And then that entire line passing through the base point of X. I'll draw maybe the top and bottom circles in red. It's not really going to matter because they all get mashed together anyway. So in our quotient map, so in the first stage, yeah, I'll do it in 2 stages. First stage is just we pinch the top and bottom. And we still have our line going through the base point of X. And then the next stage is we pinch down that line. So when you pinch down that line, think about all of these other lines coming from the cylinder from the North Pole to the South Pole. Once we take this entire line and collapse it down, these are going to be lines starting from the base point and going back to itself. So here is our new base point. And the rest of the reduced suspension is going to look like this. So here's our copy of X sitting inside the reduced suspension. And the rest of it is going to be some parametrized family of circles. Basically, for every single element of X, you get one circle, and they all pass through the same base point. So, if you have a map from the suspension of X to any other space Y, you're actually getting a map of a bunch of loops into Y. One loop for each element of X. So that's the same thing as maps from X into loops of Y. That's the loops suspension adjunction. So I'm using that here, and this is a natural isomorphism. So, yeah, so take a look at this. And in particular, since this is only picking up stuff in the base point component, let's say for X connected, this is the same as maps into the base point component of this twofold loop space. So these two things are both representable functors on the homotopy category. So by the Yoneda lemma, since this is a natural isomorphism, the Yoneda lemma is telling us there's a homotopy equivalence from BU to the base point component of loops squared BU. So by invoking representability, you actually get a topological statement about the topology of the classifying space. So this is also called Bott periodicity. So we're not going to need this, I just think it's really cute, so I wanted to include that as it's not all just abstract algebra, sometimes some real topology bumps out into out of the ether somehow. And there's also the unreduced version. So this is talking about reduced cohomology for K-theory. We also have, so for unreduced K-theory, we had that was classified by Z cross BU. You just add in a rank. And so we also have a homotopy equivalence from that to loop squared of Z cross BU. So in particular, if you loop BU twice, you end up having integer many components, and each of those components is a copy of BU. Okay, so that's what I wanted to say really quick about Bott periodicity, or at least those versions of it. Anyone have a question? A little bit. So now I'm going to mention something really briefly about how K-theory is also a cohomology theory.
I have a question.
Sure.
About, am I misunderstanding I think, are these relations correct?
Maybe not.
Isn't this, if I use transitivity, do I not get everything as Y0T is going to be is going to be related to y0 of 0, which is going to be related to y prime of 0, which is going to be related to y prime.
No, I think transitivity, you're only going to find, like, you can use transitivity inside of this.
Yeah.
Like, you can't use transitivity to go down to here and then, like, over to there. So, like, you're only going to have, transitivity is only going to let you go between things that have the same, have t-coordinate 0, or between things that have t-coordinate 1, or you have, if you want to change your t-coordinate, you have to find your way at y0, and then you're stuck on this y0 track as you change your t-coordinate between 0 and 1. There's like no other way to leave that subspace with these relations, I don't think. Unless I wrote down something dumb.
Maybe I'm not thinking this one.
Okay. Yeah, if you can find a mistake, then let me know. So K homology is, so I'm just going to say that K XA is a contravariant functor, homotopy functor. So if you have like a homotopy of good pairs, then it preserves the value from good pairs to abelian groups. Okay, so here's an interesting fact. It's kind of nice, but we haven't needed to use it. Well, I mean, we have, but secretly. So if you consider KXA, remember these were, right? These were K cycles where this is a homomorphism from E to F, isomorphism over A. You can just go ahead and forget about the A part, and you can just take their difference bundle, like the virtual bundle E minus F. Forget about this isomorphism business. This is a perfectly good bundle, or K-theory element in the K-theory of X. And you can just pull it back to A as well. So you can take E restricted to A minus F restricted to A. And you can see that, well, since if you're coming from here, you're isomorphic over A, so this class is going to be 0. And if that's the other way, is true as well. So this is an exact sequence. So for cohomology theories, we would have something like, you'd have this long exact sequence for a pair. So you would go this way and, you go this way to the pair and increase your degree by 1, and then have 2 more, and then increase degree by 1, and so on and so on. But here we haven't actually defined anything other than just K. We don't have any numbers associated to our K theory. So what we can do is we sort of impose the fact that it is a cohomology theory.
So this is exactly this phi restricted to A's identity.
Or is an isomorphism.
Is an isomorphism.
So whenever you have two isomorphic bundles here, their difference is 0 in K theory.
Okay.
Yeah. And showing exactness the other way, it's probably also easy. I just didn't want to think about it too much yet.
Also, by homotopy functor, you mean like it's invariant plus 2, like if you have homotopic spaces.
Yeah. So if you have a function of pairs from XA to YB, and you have like a homotopy of that function of pairs, then it induces the same homomorphism on the relative groups.
Okay. Also, I found my mistake here.
Okay.
I understood this as like an like this, as like a quotient by an equivalence relation, but you're questioning like this is by subspaces. The first one defines a subspace, like
Yeah.
okay, because I thought it was like you're taking like the smallest equivalence relation defined by these relations, but it's not that. It's
Yeah, I mean it is in the sense that it's like the two things are equivalent if they're in the same sub.
yeah,
that one.
but
Yeah. Okay.
okay.
Yeah. No, exactly. Okay. So one thing I don't think. Yeah, I'm not sure if Francisco mentioned this, but any cohomology theory has a suspension isomorphism. Meaning, so if you're looking looking at the cohomology of some space X, and in the reduced version of the cohomology theory, there's always some like product with an interval element type of thing that lands you in the cohomology in degree 1 larger of the suspension of X, and this is an isomorphism. And so what we could do is do something silly and try to define K-theory in terms of the suspensions of our spaces. So if we already knew, say, the n-fold suspension of the K-theory of X, we could try desuspending n times to get the K-theory in degree minus n of X. So this would allow us to define K-theory in negative degrees, which is weird because we don't normally see cohomology in negative degrees.
K0 being the point that we know.
Yeah. So this is going to be by definition. Yeah. K0 xa is going to be by definition just k of xa. And so the same for the reduced. Yeah. So this allows us to put K-theory in negative degrees. What about positive degrees? Well, this thing I'm about to erase is telling us how to do that via the Bott periodicity. We can always artificially add or remove two suspensions from our reduced K-theory of X and get the same thing back. So this allows us to take our negative stuff and just lift it up to positive degrees. And this is sort of implemented the following way. So Z, remember we had our more regular K-theory of a point with Z. This is the reduced K-theory of S0. By Bott periodicity, right, this was equal to the reduced K-theory of S2. So this is Bott, or rather the fundamental relative product theorem. And then if we have our suspension isomorphisms, we know that this is K minus 2 of S0. So this is by suspension. And we can, just treat this as the unreduced K minus 2 of a point. So what this is saying is, here's another incarnation of Bott periodicity that comes out of trying to treat this as a cohomology theory, is that the K-theory of a point in, let's say, negative degrees is, it's just a polynomial ring generated by the Bott class. So like in degree 0, you have a Z, which is b to the 0. Got a 0, and then you find b there. Then you find a 0, and then b squared. Da, 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 da. So as a ring, right? So this is as a ring. The negative degrees give us this. So how do we impose positive degrees? Well, we can just put a B inverse in degree positive 2, and then just say that this ring is the Laurent polynomials on the Bott class. And then Bott periodicity is implemented by taking a product with this Bott element in the minus second K-theory of a point. So you can use this and its inverse to push things up and down. So Z in even degrees. 0. So then for X, we would say that K of n of X is isomorphic via multiplication with the bot element of the right number of times. This is k0 of x. Let's use reduced, it's more correct. If n even and k minus 1 of x. So this is the really surprising thing about K-theory, is that it is a generalized cohomology theory. So some time ago, when you defined cohomology theories, you said one of the things on our grocery list is we want it to be, when you evaluate it on a point, you want it to be concentrated in degree 0. So K-theory is a generalized cohomology theory in that evaluating it at a point is most definitely not concentrated in degree 0. It's arbitrarily unbounded above and below. But the really interesting thing about it is that it's a 2-periodic cohomology theory. It's not just some random stuff. It just repeats every 2 degrees. So similarly, and I won't be able to talk about it, KO, which is real K-theory, is 8-periodic. When you turn it into a cohomology theory, and symplectic K-theory is also 8-periodic. But it has a different structure. This is the most complicated structure. This one's only slightly, it's just the same structure, but it's more spaced out, essentially. Or I forget, actually. It might be complicated too. It's less complicated than the real one. Okay. That's what I really wanted to say about bot periodicity. A good thing about being a cohomology theory, though, is you get tools like Meyer-Vittoris theorem in order to calculate things. And you get stuff like a Tia-Hirzebruch spectral sequence. You can actually use this to compute the K-theory of complex projective space immediately. It's Brook, but I'm not able to do that. That's all I wanted to say about that, and then I'll go into the second half. Yes, good time. Okay. Yeah, so this part is not going to be important for what I'm about to talk about. It would just be a shame to talk about K-theory without mentioning the fact that you construct this cohomology theory out of it. And it seems really artificial and weird to just impose that it's a cohomology theory. But the fact that it's represented by BU, and this theorem is telling us that BU is an infinite loop space. And so already when we're here, we've arrived in the realm of stable homotopy theory by finding that BU is an infinite loop space. So this K-theory isn't just some arbitrarily, imposed thing. The 2-periodicity we see here that we've arbitrarily imposed is just coming from the 2-periodicity of this representing spectrum in the background. So it feels fake, but then it turns out it isn't. It's actually something that we're discovering rather than imposing. Okay, so part 2. I'll start with the big scary statement and then I'll explain the pieces, and that should take up the rest of our time, I think. Okay, so let D, start with M, is a closed manifold. So it's compact and there's no boundary. There's a version of this theorem with boundary, but it's a lot harder. It's called the Atiyah-Patodi-Singer index theorem. So we're going to focus on closed manifolds. And we're going to let E0, E1 be smooth vector bundles. It's not hard to imagine what I mean by a smooth vector bundle. You just require the transition functions to be smooth. And let's now the words start. Let's D from sections of E0 to sections of E1. Let's take this to be an elliptic operator. underline that because we don't know that yet. Then, the analytical index of D, which I haven't defined yet, is equal to the topological index of the symbol class of D. So the symbol class of D needs a definition. It's an element in K-theory. We'll see exactly which K-theory. So we'll have to define that, and we'll also have to define the topological index. So, but both of these are numbers. They're both integers. The T.S. Singer index theorem is really just saying that there's these two very strange integers that we've concocted, and it turns out that they are the same. On this hand side, we just have some very strange differential operator doing some analytical things, and we get an integer because this turns out to be the difference between two dimensions of vector spaces. And this is an integer because this comes from Bott periodicity. We managed to form a K-theory element of D in the appropriate way, in the K-theory of the appropriate space, and then via a number of homomorphisms, we end up coming to something which is isomorphic to the K-theory of some 2n dimensional sphere, which by Bott periodicity brings us back down to the integers. So the fact that these should be related at all is going to be really surprising when we actually get into the details a little more. Okay. And this gamma is the space of smooth sections. I think we talked about that previously a few times. Okay, so let's start talking about what these words mean. So I'm not going to define a differential operator on a manifold. I'm not sure if you are going to get to that next. Yeah, okay. So I'm going to say next time, I'm going to define a differential operator. I can at least give a hint about where it lives. I need a different piece of paper. Yeah, essentially it's something that takes sections of one smooth bundle to sections of another smooth bundle, say of order K. The main idea is just that it locally looks like a differential operator acting on these sections. Something that would be acting on things that kind of look like they're going from Rn to Rm, where n and m are the ranks of these bundles. So just imagine locally what differential operators look like, and imagine there's a global thing that does that. So for example, something we've seen is the exterior derivative on the de Rham complexes. So these are the sections of the alternating bundles. So these really are spaces of sections of something. This is an order 1 differential operator. Probably one of the more important ones that you'll ever encounter in your life. At least it's very fundamental. And a connection on a bundle is also an order 1 differential operator. But I don't want to get too tied up in these definitions, if we're just going to talk about them a bit more next time. Okay. Now there's something kind of perverse you can do to a differential operator. Oh, no, I'll say it like this. No, yes, I have to say the thing I was going to do first. Okay. So let's make an abbreviation Let's just call this gamma 0 and gamma 1 so I'm not writing them down all the time. Okay. How do I convince you that this is a good thing to do? All right. So there is a symbol for a diff operator. And what does it do? It's kind of weird, but it does. So imagine you have your cotangent bundle with projection pi. So T star M mapping to. So our symbol of our differential operator, no, I don't like that, it's SME, so it's not like confused with symmetric. Yeah, I'm doing it there. Good. So this is going to take too much to explain. Okay, so let's take this bundle. So imagine that we take this bundle and pull it back to itself along pi. So what is this? Remember our definition of a pullback on probably way too far over. Can the camera see here?
See it, yeah.
Okay. So remember the pullback was going to be the set of all y comma psi in M cross tangent bundle so that psi is in the fiber over y. So this construction is a convenient way of thinking of all pairs of an element of our manifold along with an element in our cotangent bundle over that point. So a covector over y. So the symbol takes such a pair, an element in our manifold and an element living over that point, and it spits out a homomorphism, a linear map between these spaces of sections. Space. So this is what it is going to end up doing, and how do we actually define such a thing? So what we do is first choose a section, S, in our domain, with whose value at y, or how do I do this? Yeah, okay.
I have a question. Isn't the pullback supposed to be pairs of T star M cross T star M? Because I want to be a bundle over T star M, right? So it should.
Yeah. Okay, so what did I do here? So it's probably the wrong thing to think about. How would I talk about this then? You could. So it's not really the right domain. Shoot. Yeah, I was trying not to spend too much time thinking about this, and then I thought about it for a while, and I thought I knew what was going on, and now it turns out that I don't. Are you going to need the symbol class in your talk? Or
I can define it. I don't remember the definition. I haven't heard my talk yet, but I can talk
okay.
about that.
You're going to be able to give a much more comprehensive talk about this. So do you remember at least like what the domain was? I know it takes some data and it spits out something.
Like for me, I remember it has to be on the base manifold. Like part of the, you do need like a base point in the manifold.
Yeah, so I can write down kind of like the formula without thinking too hard about what the things are. So you start with something in your manifold and something over that. So this is living in the cotangent space over y. And then you take an element E, which is living in a section of your first bundle. And this is given by some silly formula with a power of I out front. Take your differential operator and you apply it to something like this. So you have f is a function on your manifold so that the differential of f is equal to psi over y. And you pick an s in your gamma naught so that the value at y is equal to the e that we're plugging in. And then you take the kth power of at times s. And now you get a new section scaled by whatever stuff is coming from f, and now you can apply that to y. And this is going to be in our gamma 1. So somehow it takes this data of an element in the manifold and a cotangent vector over it, and it produces a homomorphism between the two spaces of section. Does that sound roughly correct?
Yeah.
Okay.
Yeah, but I think you can fix the domain pretty quickly, right? Because your S.
It's just T star M, right?
Yeah.
Yeah.
It would just be T star M.
Yeah, like you don't really need the Y because like if you just say like C is in T star M, right?
Yeah, I guess, yeah, this is y is redundant data because it's just pi and c. Yeah. So what it's really doing, it's a good point. So symbol of D is just going from the cotangent space to E0. Interesting. Okay. So the idea is that some data in here tells us kind of how to construct an operator from going from there to there using D as a formal kind of differentiable input type of thing, which I'm not very comfortable talking about at all, so hopefully Francisco can say more next week. I just wanted to write some words down because I need to justify this big, weird, scary statement. And the following definition. So definition, now we can talk about an elliptic operator. So D, if this is a differential operator, is elliptic. Let's say elliptic at x and m. If when we take the symbol for D and restrict it to psi, yeah. So we can treat this as a fiber, as a map between the fibers, if we have a fixed base point. This should be invertible whenever psi is not 0. And D is elliptic if it is elliptic at all x. So an example would be the exterior derivative on the circle. Yes. Okay. So this might make some of my other notes not entirely correct now. Let's see here. So this is a nice definition. So the first thing that's a consequence of ellipticity D elliptic implies that D is Fredholm. So this is a theorem / definition, i.e. the dimension of the kernel of D and the dimension of the co-kernel of D are finite. So this is interesting. So this means, so these spaces of sections are very infinite dimensional, but being elliptic means that it's actually rather close to being an isomorphism between the two of them. It only fails to be an injective with finite order, and it only fails to be surjective with some finite order. So the difference between these dimensions, this is the thing that we're going to be interested in. So for F, a Fredholm operator, define the index, the analytic index, This is just the difference between these dimensions. lots of neat theory about Fredholm operators and their indices. And if you want to really dive into index theory and understand any of the proofs, you'll learn things like it's a homotopy invariant. It's actually locally constant. I don't know what I mean by that. What do I mean by that? I'll just say it's homotopy invariant. If you have like a path through the space of Fredholm operators, it's possible that their kernels and co-kernels can change dimension, but the index actually has to be the same. It's very strange. And that's really important for the K-theory proof of the index theorem. Okay, so we have a Fredholm operator, and so we have an analytic index. So now I've justified the left-hand side of the Atiyah-Singer index theorem. I've told you what is an elliptic operator and what is the analytic index. It's just a difference between these two dimensions, and so therefore by definition, right, it's an integer. So the hard part is going to be explaining the right-hand side. So we've mentioned what a symbol is, something that takes each point in the cotangent bundle and produces homomorphisms between E0 and E1. So the first challenge is going to be to extract a K-theory class out of that. And now that I realize I got the domain wrong, let's see. How does this actually work? Recover from this. Well, I can start at the end and see if I can work my way backwards. So what I know about later is we're supposed to find that the index, that the symbol class lives in the compactly supported K-theory of the tangent bundle, not the cotangent bundle. Let's see. Okay, well, sure. Let's divert the definition of the symbol class of D for now. The more meaty part is the topological index part. It turns out to be a homomorphism defined on K-theory that you have to define in several steps. So I think it's more important to focus on that than to try to remember how the symbol class finds itself incarnated. Okay, so in order to really understand that, we're going to need to introduce a new kind of K-theory, because we're talking about bundles now defined over cotangent bundles, and these things aren't compact Hausdorff. But all of the K-theory that we've talked about so far has been specifically for compact Hausdorff spaces, what we've called good. So you can define slightly more generally. So for X locally compact, so this includes, Euclidean spaces, tangent bundles, any vector bundle over a locally compact space is still be locally compact. Define compactly supported K-theory This is going to be very analogous to how we define relative K-theory. You take alpha E F phi is a compactly supported cycle. If phi is an iso outside of some compact subspace. So the idea is that you have this pair of bundles E and F, and their only difference is over some compact subspace K. And so K sub C of X is analogously to had before. You define concordance classes of this. You define it to be acyclic if phi is an isomorphism globally, and then you take the concordance classes of compactly supported cycles modulo those acyclic ones in order to define this group compactly supported K-theory. So one way you might think about this is if you have a compact subspace K, you could take the relative K theory of X relative to X minus K, right? So it's an isomorphism outside of K, meaning it would give you a relative class. And using an ordering, a partial ordering on the compact subsets, you would get a sort of a direct limit diagram whose, well, since these are good pairs, the limit is going to give you the compactly supported K theory. So that's one way of incarnating it out of things that we've already defined, but it's a lot easier to just define it in terms of compactly supported cycles.
I have a question.
Yeah.
Why? Because you're saying x comma x minus k is a good pair, but x minus k is an open set.
Yeah, no, that's a good point. Yeah, maybe just strike that. I was thinking about ordinary cohomology where you can define it as like a limit. So that wouldn't make sense because you're right. This is not a good pair. That's exactly right. What could you do? And you can take the closure of this, I guess.
You do that.
Yeah. Yeah, so I'm not going to just forget I said anything because it was wrong. Don't worry. We're going to take that incarnation of compactly supported K theory, and it also might be incorrect. One thing that is true, though, is if XA is a good pair. So this is kind of interesting. So the relative K theory of X comma A is in agreement with the compactly supported K theory of X minus A. So this difference does make sense. This doesn't have to be closed because we're taking compactly supported. So this is a useful result. Okay. So this is the tool that we're going to use in order to well, basically discuss most of the things from here on out, because it's more general than the K theories that we were already working with, and a lot of our constructions are over these non-compact spaces anyway. So first of all, let's revisit Bott periodicity in this context. So let X be R2, and let's identify it with the complex plane. And we're going to let B, surprise, be the cycle represented by, okay, we take two copies of the trivial C bundle over itself, and our action is going to be multiplication by the point that we're living over. And this is going to be an element in the compactly supported K theory of R2, where we've identified R2 with C. I'll just write it like this so it's less confusing. So this only fails to be an isomorphism at the point z equals 0, which is certainly compact. Everywhere else this is an isomorphism. And modulo signs that I should be caring about, but I don't have the energy to care about them today. So this could be z or the conjugate, but either way we'll call this the Bott element for compactly supported cohomology. K theory, sorry. And the Bott periodicity theorem is then saying there's a product map going from the compactly supported K theory of X by the Bott class to compactly supported K theory of X cross R2. So in particular, if you plug in X is some Euclidean space, right? This is telling us that the compactly supported K theory of N is Z if N is even, and 0 if N is odd. So this is yet another incarnation of Bott periodicity for compactly supported K theory. Yes, and then there's a very peculiar, I'm going to leave this here. Sorry about that. Should have written that on the board. There's a sort of peculiar notion of wrong way map. There's a wrong way map for compactly supported K theory. So if U subset of X is open, then we get a map from compactly supported K theory of U right? If it's supported on a compact subset of U, then it's supported on a compact subset of X. So let's call this inclusion J. And we get something called J bang to going the wrong way. So K-theory is contravariant. Map should be going the other way. This is going the wrong way. We tend to call things like this, or at least in Germany, a Umkehr map. It's like this, meaning wrong way map. And in terms of functoriality for compactly supported K-theory, I neglected to mention this, this is functorial for proper maps. In general, it's only functorial for proper maps, which are ones where the inverse image of a compact set is compact. So you can't just have any map from any space to any other space and expect it to respect compactly supported things, because you might be packing too many things together in your map, so that if you have compactly supported things downstairs, its pullback might not be compactly supported anymore unless your map is nice enough to preserve compactness on pullbacks. What else? There's also a Tom class, compactly supported Tom class. And I should just say real quick, because we're going to need it. So if we have V to M complex vector bundle, so we have a THK to be consistent with the notes. This is living in the following pair space. So usually this lives in this space of pairs. If you choose a metric, you can define the disk bundle of V and the sphere bundle of V. And the Tom class typically lives here. It was the wrap up of the exterior bundle pullback. So this is the relative. Or now that we have compactly supported K-theory, we can think about it living in just the compactly supported K-theory of the total space of V itself. So it's much more convenient. You can imagine that it's supported around the zero section. You can choose like a little bump function around the zero section of V, where M is compact maybe. Yeah, let's say M is compact. So you can choose this tiny little bump function around the zero section, and you can imagine your Tom class is only supported in that little thin band around the zero section, giving you a compactly supported class in the total space. And then we get a Tom isomorphism. So this is going K-theory M, if it doesn't need to have a boundary, to the K-theory of the vector bundle. And we're sending alpha to just the exterior product with the Tom class. Something probably has to be pulled up. Imagine you would do something like, yeah. So this is interesting. You have to be careful because the pullback of alpha, like I said, this projection map of this bundle is not proper. So the pullback of alpha doesn't necessarily give you an actually compact supported thing, but when you take the product with something that is compactly supported already, you sort of get rid of all of that infinite stuff. You're incorporating the compact support here into the whole product so that you can take this non-compactly supported thing and produce an actual compactly supported thing using that Tom class to kind of truncate it and to do all of the other magical things that the Tom class is doing. Okay, so we've got compactly supported K-theory. Now we want to define what is the topological index. And the way I'm going to do it is I'm going to start over here on the left. I'm going to start writing down this sequence of homomorphisms, and then I'm going to justify them one at a time. I've got a bit of time, so I shouldn't dawdle too much. Okay, so here's what our topological index homomorphism is going to look like. Maybe I do need to do the tubular neighborhood theorem first. no. Okay, sorry, scratch that. I'm gonna go back here and write stuff down here. Sorry about that. No, I'm sticking to the plan. Sorry again. It's more fun if I do it this way. So let's let n be closed. So choose n embedding of m into Rn. So this is an exclamation mark statement. Not clear why we can do that. Choose a tubular neighborhood. We'll call it U subset of Rn. That's an exclamation mark statement. And then we have that, let's see, what would we say here? So tubular neighborhood means that U as a total space of a bundle is isomorphic to the normal bundle of M. If we take TU, the tangent bundle of U, as a submanifold of this is sitting as a submanifold of the tangent bundle of Rn, which we can identify with R2n. And this is a tubular neighborhood of the tangent bundle of M in R2n. Okay, so far so good. And has Tom class, let's say THM. So what do we do? So we have top end. We're going to start at the compactly supported K-theory of the tangent bundle of M. And then via the Tom isomorphism, which I should give a name. Yeah, I should give a different name to the isomorphism versus the class itself. I'm going to call this big TH. Okay, sorry about that again. So this is big TH, Tom isomorphism, going to the compactly supported K-theory of tangent bundle of U, which is the normal isomorphic to the normal bundle of this guy. This is an open subset of this, and so we get a push-forward map to the compactly supported K-theory of R to N, which by Bott periodicity, we said this is isomorphic to Z. So this whole homomorphism is called top end. Takes a compactly supported element of the K-theory of the tangent bundle, and it gives us an integer. In fact, so the only things that I would have to justify in this statement is the choose an embedding. I think I'll just wave my hands and say this is the Whitney embedding theorem. These are like differential topology background stuff, so I don't really have time to go through it. Whitney embedding theorem just says that given any manifold, you can smoothly embed it into Euclidean space of at most twice the dimension. And the tubular neighborhood theorem,
It's at least twice. Because usually it's easier to prove it that you can embed it to 2n plus 1.
yeah, but you can also embed it into smaller dimensions sometimes. You never have to embed it in more than 2n. That makes sense. So here's a tubular n-hood theorem. Tubular neighborhood theorem just says that whenever you have a smooth embedding into some manifold, you can find an open neighborhood of it, which is homeomorphic to the total space of the normal bundle. And the homeomorphism sends the zero section to your subspace sitting inside of it. So it's just like a geometric model of the normal bundle. So you can use it as kind of in order to transfer things from your larger manifold to your smaller manifold. So those are topological black boxes. I'm okay with just saying, go read a book. This is the topological index. So the Atiyah-Singer index theorem is saying if you take a differential operator and if you interpret the symbol class as an element of this K group, so that's going to be on my list of questions of how to do. I don't remember how to do that, so unfortunately I'm not going to be able to present that. How do we find the symbol of D as an element in compactly supported K theory of the tangent bundle? Because the way that we wrote it down over there, it was like it involving the cotangent bundle. And yeah, not clear to me off the top of my head how to go from this expression to one of these compactly supported things. So this is kind of a big thing. If I think of something before next time, I might try to mention something. Right. So the Atiyah-Singer index theorem. Modulo this, we haven't done this. But at this point, we've defined all of the terms. So I have stated the Atiyah-Singer index theorem. Okay, so I'm not done yet, but does anyone have questions I might be able to answer about that?
Maybe you just pick a metric on that.
And get an isomorphism between the two. That's probably what it is, because honestly, most of the time we're picking a metric for all of this stuff anyway. So it could just be you pick a metric and you don't worry about cotangent stuff anymore. Not sure where to get compact support from. You might just have to do, like I said, choose a compactly supported function and just like truncate your thing away from the zero section. Something like that. Yeah, I don't really want to speculate too much because I'm sure it'll say a lot of wrong things.
I think I can try to figure that one out. I think I can probably talk about it next time because I know that. I'm not going to say more because I don't want to say something wrong either.
Yeah.
So I can try to address it next time.
Yeah, I feel like we're on thin ice right now.
Because I feel like I can feel the connection. I just don't want to say something wrong.
Yeah, exactly. Yeah, this is when things just start to get like a little too many layers of like and pulling back and things like this. Okay, so now let's move on to the practical version. So there's a cohomological formula. Hey. So I just explained the statement of the Atiyah-Singer index theorem.
Perfect time.
Yeah, so now we're going to do the if you thought you didn't understand that, just wait until you see this. So this is the cohomological formula for the Atiyah-Singer index theorem. And I have to decide if I want to just write it down right away or I'll motivate it. Why don't I motivate it? Okay, so we have this top end homomorphism. Moving from here, this is a Tom isomorphism to the tubular neighborhood. And we had this open inclusion getting us to R2n. And then Bott periodicity, this is multiplication by b to the minus n. This gives us down to z. Okay, so this was our homomorphism. We have an elliptic operator. We extract our symbol class. We plug it in here, shoots us out this end, and it spits out the analytic index of our elliptic operator. So K-theory is not very hands-on, not very computationally convenient. We'd like to do an analogous thing in cohomology. So there's also a compactly supported cohomology, which you can just take as like Durand cohomology, where all of our forms are compactly supported. So that's something you can just do. And the coefficients of this theory are inherently the real numbers. But in this K-theory, or cohomology theory, you still have Tom isomorphisms. So now it's going to increase the degree on the star, but since I'm writing a star, I'll just let you absorb that into the notation. Compactly supported de Rham forms, when you have an open inclusion, it's the same principle, like it's still compactly supported in the larger space. So we get to be here. And then what we can do is, given a compactly supported form on R2n, we can integrate it. These are essentially going to give us, you can integrate it and get a real number. Okay, and this z sits inside this r. And we'd like to be able to relate these two sequences together. So the most natural way to do this is with the Chern character. So this is sort of a story for another time, but what this is, it's a natural transformation. It's actually been finely tuned to also be a ring homomorphism. Exclamation. It goes from K-theory, or even compactly supported K-theory, of X to cohomology, possibly compactly supported, of X with rational coefficients. The Chern classes naturally have integer coefficients, but they sort of have the wrong property. They take a sum of bundles to a product of classes. Chern character has the property that it takes a sum of bundles to the sum of bundles. Sort of the sum of Chern characters. And similarly, like it's a ring homomorphism, so similarly with the tensor product. But this happens at the cost of introducing rational coefficients into the formulas for this thing. So we can go and take our K-theory sequence and we can just jump down with the Chern character like this. Okay. So it's totally not obvious, but if you do the Chern character and then you integrate, that's the same thing as doing Bott periodicity. Totally not obvious, but this squared actually does commute. Somewhat more obvious, since both of these maps are induced by continuous functions, this squared does commute. And totally not obvious, but this squared does not commute. So if we wanted to say, take our K-theory element and evaluate it through cohomology by just saying, all right, take its Chern character, punt it down this line, and then integrate it over the fundamental class to get what is actually going to be an integer, because it would agree with the top line. We can't do that. We can put this one down and get the same value here as we would by going there, but by non-commutativity of this, our hands are a little bit tied. We can't just do this automatically. So the thing that saves us is that non-commutativity is somehow, in a way that I don't really, not prepared to spell out, natural in the normal bundle of M. Meaning, like, if we had another manifold and we had another situation like this, and like sort of commuting embeddings, and we compared the two squares, we would find that sort of their difference to commute on this square would pull back to the failure to commute in the other square. It's not a very good explanation, but the outcome is that there is a characteristic class. You can say called mu of mu m, so that if you do Chern class after the K-theory Tom isomorphism, let's put a H and a K just to make sure that we know the difference. This is the same as doing the Chern character, or how do I say this? What's the best way of saying this? Let's take an actual element. So the Chern character applied to the Tom isomorphism applied to alpha is the same as taking the Chern character of alpha cupped with this mu that has nothing to do with alpha, and then you apply the cohomology Thom isomorphism to that. So this is the precise way in which this characteristic class that only depends on M, and particularly its normal bundle, you use this characteristic class to fill in this square so that it does commute. It's kind of a scary expression, but at this point, that's really the name of the game. You can't really alleviate any of that. This is just what it is.
I have a question about this class being dependent of the normal bundle, depend on M. So if I take a different embedding to a different, like I don't have to take R2N, if I take a different to a different N, does that still work?
Yeah, that comes down to like the commutativity of this square. So if you chose a different embedding in a different normal bundle and stuff, everything on the right-hand side would still work. This beta, it turns out like there's a bot class associated to a vector space, and if you add two vector spaces together, you multiply their bot classes. So this type of phenomenon ensures that, like, if you had chosen a different dimension, this square would still commute. Then, like, the embedding comes down to here, I guess. Well, this is actually just about the normal bundle. This is the part that depends on the embedding. This would still commute because we have these j's. So all it really comes down to is this square is failing to commute because of the Thom isomorphism for the normal bundle of M. So that's why this mu actually only somehow depends on the normal bundle of M. Because it's sort of like every other part of the picture over here, like there's other geometric reasons why that stuff is still a commutative square. I think. Yeah, I'm not totally expert, so watch out for that. Okay, so we have this mu. It would be nice to have something in terms of the tangent bundle of M, though. So here's another black box. There's another characteristic class called the Todd class. So that, and this is something that is a characteristic class for complex vector bundles. Yeah, this is where my notes don't really work out very well because I was confused while I was reading it. I'll just write down verbatim what I was writing verbatim from the notes. If you take your normal bundle and complexify it, this mu is the same thing as the Todd class of the tangent bundle complexified. So this lets us replace this expression with something that depends on the tangent bundle of M, rather than the normal bundle of M. So in terms of this, in fact, there might even have to be something like you have to pull this back. The formula that I got out of the notes is now saying that the topological index of some class alpha is going to then be, all right, we're going to integrate, how's it going to work? Yeah, this whole thing is, how does this work? I'll just write it down. There's no way I can really explain this. So we're going to have the churn character cup with the pullback of this Todd class. Does that look right? Sort of. So you take the churn character of your thing down to the cohomology of the tangent bundle, and then you're cupping with your thing that makes sure that the thing commutes. Yeah, I seem to be skipping a tremendous amount of steps here. Okay, I am definitely skipping a lot of steps. This is one step that you get to. And then the final step is we want to make sure, we want to get rid of this tangent bundle factor, and we want to just write this in terms of an integration over M. And we're able to do this using the Thom isomorphism for the complexified tangent bundle. Wait, why does that bundle have a Thom isomorphism? Ah, because it's orientable, yeah. So M orientable means that there's a Thom isomorphism for its tangent bundle. Thom of M, I'll just write from the compactly supported cohomology of M to the compactly supported cohomology of the tangent bundle. So instead of starting with the tangent bundle over here, we could have actually started with M. and something about the Tom isomorphisms are compatible with like module morphisms over the base space. There's a bit of algebraic topology skulking around in the background, so that this pi star ends up disappearing. And we get that the topological index of alpha is actually some terrible sign. I'm going to use D because I've already used N in a different context. So D is dim M. Is it? Or is it actually equal to the N? No, it shouldn't be equal to the N that you embedded in. No. Yes, dimension of the manifold, integral over M. Now we're going to have this Tom isomorphism inverse of the Chern character of alpha cupped with the Todd class of the complexified tangent bundle. Yes. So this, if you believe it or not, you can actually use this to derive formulas for different quantities, like the Hertzsprung signature theorem is related to these L polynomials. You can use this formula to actually compute these L polynomials directly. And before I leave, I want to mention one thing with regards to spin manifolds, because I think it's kind of neat. So last thing, we're over time. So if M is a spin manifold, then in a way that maybe Francisco will talk about, it supports Dirac operator, which I'll just write as a D with a line through it, and the top end of D is called the A hat genus of M. So this was Atiyah's like original, I can just say that the index. This was like one of Atiyah's original motivations for studying the index theorem, along with Hertzsprung signature theorem, was that for spin manifolds you have this very, very famous operator, the D hat operator, or the Dirac operator. And it turns out that there's an actual expression for this using these complicated rational power series that you can derive using this formula here for the topological index. And so A hat is a characteristic class living in, well, this says that you can define it for spin operators, but the actual expression, it makes sense just in terms of Pontryagin classes. So this is something that lives in the cohomology of BS mode with rational coefficients. So the fact, right, so this is telling us, what this is telling us is that if M is spin, then the A hat genus of M is an integer. Even though you have a definition for the A hat genus for every orientable manifold. You just choose a classifying map into here for the stable normal bundle, and then pull back this characteristic class and evaluate on the fundamental class. So that's neat. This can be used to detect if a manifold is spin, but we already have something that does that called the second Stiefel-Whitney class. The other thing that's interesting about this, which you can also prove by showing that it is the index of the Dirac operator for spin manifolds. So if a spin manifold has a positive scalar curvature metric, then the A hat genus is 0. So this follows from analysis of the Dirac operator. I forget the name of the theorem. If I heard it, I would say, yeah, that's the one. But in fact, this A hat genus, which kind of appeared innocuous, well, not innocuously, but magically out of the index theorem, is used as an obstruction to tell if spin manifolds have a positive scalar curvature metric or not. There's lots of other applications of the A hat genus. In some ways, it kind of just falls out of index theory. Yeah, so that's all I can possibly say about index theory. So thank you for coming out. Yeah, it's not the best account of index theory that exists, but I don't have to do it anymore. So questions? Yeah, Daniel. We have a million questions.
What are some, I guess, if someone wants to pursue this, what are some nice follow-up topics? Maybe Seiberg-Witten invariances?
Yeah, that would be like, well, that's one direction that you can go. Before Seiberg-Witten, I guess I would look at like Donaldson theory first, because it's easier, I think.
What's Donaldson theory?
I guess
it's also like an application of index theory to four manifolds.
Right, I guess I'm asking,
forget how it works.
What does this branch off to, this?
What does index theory branch off to?
Yeah, like today's talk, yeah.
Loads of stuff. So, I mean, I mentioned this A-hat genus and how you can use this formula to compute the Herzebrook L polynomials. Those were sort of what people figured out in the 1960s. And then later there was this PSE metric stuff. This is what my advisor focuses on, is using index theory to study PSE metrics. He has a result that says for certain spin manifolds of a certain dimension and connectivity, blah, 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 you can study the space of all positive scalar curvature metrics. Each of these metrics gives you something called a KO orientation, which is, well, gives you something called the KO orientation. And the outcome is essentially that if you have, I guess he uses an R for some reason. So he has an R, M. So if this is the space of positive scalar curvature metrics, he gets a map to some infinite loop space minus D or whatever, if this is a D-dimensional manifold of the KO spectrum. So we were only talking about complex K-theory. This is the object that like represents K-theory of real vector bundles. And so the idea is, in certain cases, so this map is surjective on homotopy groups. So this KO has infinitely many non-zero homotopy groups. So what his result established is that your space of positive scalar curvature metrics also has infinitely many non-zero homotopy groups. And so this, part of his big argument was using index theory. Part of it is using this really crazy stuff called the Madsen-Tillman spectrum for spin. There's like a universal spin orientation, KO orientation coming from this, and then I think he constructs this by obstruction theory or something like that. So, yeah, so there's things, weird things you can do with PSE metrics. I guess Witten does things about calculating the dimension of spaces of Yang-Mills instantons using the index theorem, and I don't know anything about that. Francisco probably knows lots of other examples.
So at least I think that's kind of similar to what Witten does, but at least in the stuff that I do, this comes up a lot when you want to, for example, calculate the moduli space of homomorphic curves. So usually, for example, if you look at Floor theory, what you have is the Floor theory, you look at moduli space of solutions to a certain differential equation. The differential equation has an associated differential operator, so you have the D. But computing this right-hand side is horrible. So you use index theorem to compute the left-hand side, which is easy because you just have to compute its race, but the dimension of kernels and dimension of co-kernels. And that gives you, at least in the smooth locus, a dimension of the moduli space. So this allows you to count these things. So I would say, and that's similar to what you do in most like when you have all these weird invariants in physics, you want to count certain stuff, number of stuff, and you do that because they're usually defined by some differential equation, and it's hard to count what number of things solve this differential equation. So what you do is use index theorem. But that's like very applied index theorem. Like you don't need to understand the index theorem. You just need to understand
how to apply it.
Exactly. Yeah. So that's what my talk's going to be mainly about. Like, actually, I am curious about kind of in my preparation. I will try to kind of answer some of these questions. I thought it was really cool, but I understand the link with K theory. But the main focus for me is going to be applications because that's mainly what I use it for, rather than the pure abstract theory.
Yeah, whereas like I went through like a year-long course on index theory, and like I don't know any applications. Like, I don't know where this stuff comes from. Just saw a bunch of K-theory.
Yeah, so like Riemann Roch is a prime example of like how do you compute these moduli spaces. You have these generalized Riemann Roch from, let's see, a singular disk, and that's how you compute. So we're going to, at least my goal is to compute like some moduli space dimensions.
That's cool.
Yeah.
I also heard somewhere something about in TQFT's equivariant K theories up to surgery representations or something like that.
Something like that. Sure.
I don't know what that is, but it is something.
Yeah, I don't know what people mean by surgery representations.
I don't know either, but from looking at the board, it just looked like you have the same topological space, you just cut it differently.
Okay.
But I could be completely off. That's just what I saw on the board.
This is related to equivariant K theory somehow. Yeah, equivariant K theory. I didn't even scratch the surface on that. That's a different thing. I think you can just get away with talking about K theory of bundles with a G action, and then just have equivariant. Whenever you have to have a morphism, you would just require it to be equivariant. But there might be something more complicated. Because like for cohomology, like your equivariant G cohomology of your space X is fucking, you take the Borel construction and G crossover G of X where G. So this is like a weird thing. I don't think you have to do the same thing for K theory, but I'm not sure, maybe the same construction still works. It might be easier to do it this way than actually just talk about G bundles. But I don't know. I don't know that stuff really. Question.
Yeah, I know we haven't talked about the Clifford algebra stuff much, but like, is the thing about like there's only like 2 grades of K related to the fact that like you only have like 2 grades with Clifford algebra?
It's different. Yeah, so the periodicities in K theory do come from Clifford algebras. This is where, so I'm not going to be able to say, I'll just say buzzwords. There's a thing called the Atiyah-Bott-Shapiro construction. So after Bott proved Bott periodicity, there was like a couple years later that they came up with this purely algebraic reformulation of it. So that, like, when you take your K theory of a point and you treat it as like a graded ring, that this is something about modules over, I don't know, if we say like minus n or something, modules over CL or n modulo those that extend. This is almost definitely wrong. I shouldn't be writing it down at all. I'm almost certain that this is incorrect. It's something like this. There's like a theory of modules over Clifford algebras, and this is like big quotes, where like you have your modules that you're interested in, and you say, okay, the ones that extend to one more Clifford variable, let's just presume that those are trivial, and then the quotient ends up giving you the K theory of the point back. And so there's a similar construction for the other K theories. So there's the KO, KSB. And the fundamental thing that makes it work is called 1-1 periodicity. That's something you can look up. So I forget precisely what the statement is, but yeah, so this stuff, you should either go and find it in Atiyah-Bott-Shapiro's original paper, or there's also the first chapter of Spin Geometry by Lawson and Michelson. It's all just about the Clifford stuff. Spin Geometry. So there you'll find actual statements. I'm going to spell at least one of their names wrong here. I think it's Michel's. Something like that. So this is the textbook. For the longest time, this was like the only textbook there was about like the K theory version of index theory. But now, like, oh, my advisor was supposed to turn all of his stuff into a book, but his notes are from 2015 or something, so I'm not sure if he's making progress on that or not. Yes. Yeah. I think there's nothing else I could possibly say. I meant to make mention about the Attila Bot Shapiro, so I'm glad you asked about it. If there's time for another talk later, I might do that, but don't know that stuff very well, and it's not very exciting either. We'll see. All right.